So I'm Phil Thomas, and today I'll be talking a little bit about safe and fair machine learning. I see something in chat. Let me see. Just thanking chat friend. Great. So, okay, so I'll tell you a little bit about the work that our lab does. So first, I co-direct the Autonomous Learning Lab, which it used to have a different name. Long ago, back in I think the 80s, it went by a different name. And then the director of the lab, Andy Bardo, renamed it to the Autonomous Learning Lab so it would come first when it was alphabetized in lists. So hence the Autonomous Learning Lab. And that name isn't the most descriptive as a result. So in a moment, I'll tell you a little bit more about what the lab does. But I co-direct it with Professor Bruno Castro da Silva. And also in this talk, I'll cover two projects that we worked on recently in the lab to give you an idea of the work that we did. And really, this is the work of the fantastic graduate students that are in the lab. So I just wanted to recognize them. Okay, so what is the Autonomous Learning Lab? The Autonomous Learning Lab conducts foundational artificial intelligence research with emphases on AI safety and reinforcement learning, and particularly the intersection of these two areas. So what do I mean by foundational? Well, we are less interested in beating benchmarks and competing and tweaking algorithms. We're more interested in, can we change the problem setup in a way to have problems that no method could solve before, and we create the first methods that can solve that class of problems. That's the kind of what I mean by foundational projects. And the two projects I'll talk about today are examples of that. With respect to AI safety and reinforcement learning, Professor Bruno Castro da Silva, Bruno and I, we differ a little bit on this. I focus more on AI safety, but I'm of course interested in RL. My background was in reinforcement learning, whereas Bruno's the other way around. He focuses more on hierarchical reinforcement learning, especially for robotics, with interests in AI safety. Okay, so for anyone who's not familiar with RL before, what is reinforcement learning? It's a subclass of machine learning where an agent, a program or a robot is learning from feedback in its environment, and that's evaluative feedback. So what happens? We can set up RL roughly with this diagram, where there's some environment that our agent is interacting with. That agent, we can think of it for now as just a piece of software. It makes some observations about the state of the environment. Based on that state of the environment, it makes a decision. And that decision we call an action AT. That action changes the state of the world. And hence we go to ST+1, the state at the time T+1. And this loop repeats. But also at each time step, the agent receives a reward. This is just a number that says how good the current outcome was. So this is a measure of kind of how good the agent's decisions were. One other thing, the agent, the mechanism within the agent that chooses actions, we call a policy. And this is pretty much it for notation in this talk. So if you're like, oh no, this is going to be a wall of notation, this is pretty much the notation we will do for the whole talk. So a policy is that mechanism that's making decisions, where pi of SA is the probability that this agent chooses an action A when it's in state S. And so the agent's goal is to find a policy that maximizes the total amount of reward that it gets. And reinforcement learning is interesting because there are many really high impact proposed uses of RL. So first there's medicine. Within medicine, there was a Nature Medicine paper proposing the use of RL for improving treatment of sepsis in the ER or the ICU. And there the state is a description of the patient. The action A is what treatment we give, and that changes the state of the patient in the future. And then we have to decide which treatments to give. And I believe in that paper, the rewards were 0 throughout, and then 1 if the patient survives. This is because sepsis is often very severe. It's responsible for 1 in 5 deaths worldwide. Another example would be type 1 diabetes treatment. I've done some simulation work in this domain where the state is a description of the person, and the action is how much insulin the insulin pump should inject into their blood before they eat a meal in order to help regulate their blood sugar levels. The reward is some measurement of how much their blood sugar levels deviate from the ideal target blood sugar levels for that person. Other examples, long ago, back in the days of my master's, we did work on functional electrical stimulation, where we were putting probes into a paralyzed person's arm and stimulating their muscles in order to move their arm for them to some target location, where there the state is the position of the person's arm, the joint angles, the action is how much power to give, and the reward is a measurement of how far the person's wrist is from the target wrist location. Beyond medicine, RL has been proposed for serving up advertisements, so targeting ads. The state here is a description of you. The decision is which ad to show you or which class of ads to show you. And the reward is +1 if you click. And the next time that you come back to our page, we know a little bit more about you. Did you click on certain ads in the past? And so that state has changed. And also you can imagine RL relates heavily to controlling robots. So that's just proposed uses. But for all of these proposed applications, none of which have really come to fruition yet, there are serious safety concerns. So consider the following setup, where we have data collected from using one policy, that's some currently used policy, but then we use our favorite reinforcement learning method to find some new policy, PINU. So there's some current policy making decisions, doctors giving treatments in the ICU, and we use RL and it says this mechanism, this decision-making rule would be better than what we're currently doing. Okay, but there's a challenge. If that new policy is actually worse than the current policy, that could cause significant cost or harm. So if it's ads, we're losing money, but in the medical examples, this could be extremely dangerous if we're deploying a new policy that's actually worse or dangerous. So there's a need for these tools called off-policy evaluation methods, which is one of the main things that I focus on. And these methods are this black box in the middle. They take historical data D. That's data that was generated by the current policy. So how did doctors prescribe drugs in this case, or prescribe treatments? It also takes as input a newly proposed policy. So we assume some other RL mechanism, reinforcement learning mechanism, has come up with a proposed new policy, and that is given as input to this OPE mechanism. Okay, what does the OPE black box do? It takes that data as input and that proposed new policy, and it outputs an estimate of what the performance of this new policy would be. What would happen if we actually deployed this in the real world? And the key thing is this black box is not actually deploying the new policy, because that could be risky or dangerous. We don't want to change how we treat sepsis in the ICU to something that's worse in order to evaluate, is this worse? We want to figure out it's worse before we try using it. So that's what these black boxes do. And also, why is this hard? So if you're thinking about supervised learning, this is really easy to do. So if I have a model and I want to know how accurate it is, I hold out some of my data, I run my model on that held out data, and I look how accurate it was. But you can't do that in RL, because in RL, we don't have labels. So in RL, I could run my new policy and that would give me new actions, but I don't know the outcomes of those actions. I don't know what rewards would result or what states would result from those actions. My data only contains what happened under the current policy, not the new policy. So that's why this task is challenging. So there's a long history of off-policy evaluation methods in reinforcement learning. And I just want to give an idea of what exactly those methods are doing. So on the horizontal axis, we have some measure of the outcome quality. So you can think of this as we are treating you for type 1 diabetes, and how far was your blood sugar level deviating from some ideal level? And in this case, higher is better. So a better outcome quality is what we're aiming for, and lower is worse. So there is some true distribution of outcome quality. And if you're familiar with it with reinforcement learning, this axis is expected discounted return, is what this is formally. So there is some true distribution if I were to run this new policy over what outcomes would occur. And we don't know this distribution. This is what we want to know about. So what typical off-policy evaluation methods do, often based on a technique called importance sampling, is they give estimates of the mean of this distribution, the expected value. What is the average outcome under this new policy? And we've had methods that can do this since around the year 2000. And then in 2015, actually, my first paper that kind of took off was getting practical confidence intervals on this mean value. So we had confidence intervals, but they were completely impractically wide. So some of my earliest work was on getting confidence intervals for this mean that are useful, that tell us not just here's our prediction of what will happen, but with 95% confidence, the true mean performance under this new distribution will be in this interval. So we need those confidence intervals to have confidence that this policy will be safe if we were to use it. But this isn't really enough. So in a NeurIPS paper 2021, this is just this last year, called Universal Off-Policy Evaluation, we generalize this concept. So consider this gray distribution. Would this be better or worse, this distribution of potential outcomes? So for many medical examples, this wouldn't actually be better, even though the mean of this gray distribution may be a little bit higher. So our average outcome is a little bit better. Our lower tail is significantly larger. We've increased the variance. So the idea is for a medical application, these could be patients who are having horrible outcomes. We don't want to slightly increase the mean outcome by largely increasing the the number of negative outcomes counterweighed with some more good outcomes. We want to reason about these worst case outcomes. What happens to the patients in the worst case? So it's not necessarily better if the mean is higher. So for many of these applications, we need other measures of performance, other measures of what's happening. So one typical one of these would be variance. What's the variance of the distribution of outcomes? Until I think it was 2020, there were no methods that could give us estimates and confidence intervals for the variance of outcomes if you were to deploy this new policy, but without actually deploying it, using data from your current policy. We presented a method that handles variance. I think it was in 2020, the year before this paper. But in the 2021 paper, we showed how we can get confidence intervals for variance. We can also bound any parameter of this distribution. Any parameter you think might characterize the risky thing you care about for your application, we can estimate it and bound it with high confidence now. So one of those would be quantiles. So this is that the alpha quantile says that the percent of outcomes that are worse than this value is at most alpha, or is alpha. So we can find that quantile. We can also compute something called conditional value at risk, which is the expected performance given that we are in the alpha worst percent of outcomes. So this says for the alpha percent of patients where things go worst, what is the average performance? Before, there was no way for estimating or bounding this given off-policy data, given data from some current policy. But now we presented the first method that can achieve it, and we showed how we could get confidence intervals that have what's called guaranteed coverage, meaning if that confidence interval says it's a 95% confidence interval, the parameter really will be in that interval 95% of the time. For the sake of time, I'll skip over this. The gist of how we achieve this is by estimating the entire cumulative distribution function, CDF, of outcomes under the new policy, reusing that same concept of importance sampling, but in a different way, to get unbiased estimates of the CDF at different points, and then to obtain a confidence band for the entire CDF. But for the sake of time, I think I will go on to the next topic. So it was one paper that we published, which presented the first methods for obtaining confidence intervals and estimates for these other parameters. Our comparison was just empty for these other parameters because there were no other methods that could do this. So let's talk a little bit about another project which relates to fairness. As I'm sure many of you have heard in the news and just talking to other people in computer science, fairness is becoming a very hot topic in machine learning. The issue is that machine learning algorithms can make unfair predictions, for example, racist or sexist predictions. One example of this that was a news article that kicked off a lot of interest in the field was the machine bias article by ProPublica. If you haven't read it, I can't recommend it strongly enough. The gist is that in 11 states, during criminal sentencing, so this is after someone has been convicted of a crime when a judge is deciding on their sentence, how long do they spend in jail? There was a piece of software created by a company called Northpoint that took a description of the person and predicted whether they would commit a violent crime in the future. And the judge was shown these predictions to help them decide on the sentence that the person should get. ProPublica analyzed the predictions of this system and compared it to what actually happened. Did those people go on to reoffend and commit a violent crime? And they found that the system, if we just look at the people who did not go on to reoffend, the people who did not commit a violent crime in the future, the system was twice as likely to say that they would if they were Black. And so this represented a form of unfair predictions in the model. Another example, in a paper that we published, we were predicting student GPAs from their application materials to a university. And we showed that standard machine learning methods, linear regression and neural network in a random forest, would on average overpredict the GPAs for men by 0.15 GPA points and underpredict the GPAs for women by 0.15 GPA points. And this is on top of all of the systemic issues of unfairness that are built into notions of performance, like GPA is biased on its own. But the machine learning algorithm is introducing additional bias in its predictions. So one interesting question is, can we make machine learning algorithms that don't exhibit this unfair behavior? But this raises the question, what does fairness mean? Does fairness mean that we predict the same GPA on average for men and women, or does it mean that we don't overpredict for one gender and underpredict for another gender? Turns out those two definitions are conflicting. On our data set, you cannot satisfy both of these at once. But in order to start creating fair algorithms, we have to define fairness. And there are many definitions in the literature. For the sake of time, I'll skip over these. These are three. The ... is meaning to say that there are many more of these. There's a paper titled 20 fairness definitions for classification. And all of those definitions are in terms of these kinds of false positive rates and false negative rates. How often we predict yes when the answer is no, or predict no when the answer is yes, for will they repay a loan, or would this student get a GPA above some threshold if we admitted them. And there's a problem with this. Or it's actually, before I go into the problem, in our previous work, we presented a new method that allows the data scientist to choose the definition of fairness for the application at hand. So instead of us saying, this is the definition of fairness and our algorithm satisfies this one definition, we let the user pick what definition they want from a massive class of fairness definitions, infinite fairness definitions. And the person can also choose the probability delta. And we guarantee that we will not return a model that's unfair with respect to their definition of fairness with probability at least 1 minus delta. Okay, but there's a problem with this. So this paper is a wonderful paper. It is not by us. This was, I believe, the best paper at ICML 2018, titled Delayed Impact of Fair Machine Learning. And the argument of this paper is that ensuring fairness according to those standard definitions in terms of false positive or false negative rates can actually increase social inequality in the long term. This seemingly fair behavior in the long term can be bad for social inequality. So maybe these fairness definitions aren't the right thing. They help us to feel good, like we're doing something fair, but they're making the problem worse. So the real question is, can we enforce fairness guarantees that say, okay, we're being fair in some way, and we're not going to make this problem worse in the long term? And this paper showed how to do that in the case when we know exactly how our predictions of the model influence the long-term measure of impact for a person, which is unrealistic. We don't know if I give this person a loan or not, what will the long-term impact be for that person? So in a paper that's in submission now, it'll be on arXiv, hopefully within a month, titled Enforcing Delayed Impact Fairness Guarantees. Our lab showed how we can enforce delayed impact fairness constraints when this long-term impact of predictions isn't known a priori. So we're going to use data to reason automatically about the long-term impact of the decisions of the model. And then we give high confidence fairness guarantees. And the neat thing is that this blends the classification and reinforcement learning settings. So what is the classification piece of this? The classification piece is it's still a classification algorithm predicting, will a person repay a loan? Will this person commit a violent crime in the future? One thing that we did in this paper was, will this person, I think it was, have a job after leaving foster care if they're given these additional benefits? So that's the classification piece. It is a classification algorithm. But fairness with respect to delayed impact is actually a reinforcement learning problem. Delayed impact is this, in the future, here's the outcome for that person, which is shaped by the decision that we made. That's like a reward in the reinforcement learning context. And our classifier is more like a policy. Predicting labels is choosing actions that influence that person's life. So the exact same off-policy evaluation tools that I was talking about before are what we're bringing in here to ensure fairness. So we're combining reinforcement learning-based fairness constraints with supervised learning classification algorithms. And with that, I'm a minute over. Sorry to eat into your time, Hava. Are there any quick questions while Hava gets set up?